Welcome all. So, today we will continue with the single degree of freedom analysis. Last time we saw the single degree of freedom analysis applied to the undamped systems. We saw it applied to the systems having a forcing function. Then we looked into the equivalent mass, equivalent stiffness. Okay, we did one example of an equivalent stiffness calculation for a simply supported beam. Now we will continue ahead. So, today we will take up one more example. Last time we formulated our forcing function using the deflection equations. Okay. So, today we will try to formulate the shape functions using other types of equations. Okay. So, here we have been given a uniform cantilever tower of length L. So, there is a cantilever tower, it has a length L, okay, and it has a mass per unit length m. Okay. So, mass per unit length is m and it has a flexural rigidity EI. Okay. It means that the cross section is constant throughout and the material is constant. Okay. We have to formulate the equation of the motion from the system. Okay. And here in this particular example, the forcing function is then ground excitation. Okay. And we have to determine the natural frequency. Okay. So, earlier in the previous example, we saw that we can formulate the equation of the motion using the deflection equations. Okay. So, what I can do is that one way is to choose my degree of freedom first. Okay. Let us say I am choosing the horizontal displacement at the free end, okay, y at x equals to L if I am calculating x from here. Okay. So, then what I can do is that I can take this system, okay, put an equivalent load here, okay, calculate the deflection equation, okay, y deflection equation. Okay. So, that will be the numerator of my shape functions, and the denominator I can put y at x equals to L. Okay. So, this is the chosen degree of freedom. Okay. So, this becomes my denominator, and this way I can formulate the shape functions. Also, what I can do is that I can choose the shape functions using any other approximation. Okay. So, here I am choosing a cos type of function. Okay. So, here 1 minus cos, I am choosing my 1 minus cos function. Okay. So, this mimics this same type of shape. Okay. There is a positive side to it and there is a negative side to it. Okay. If I am using this particular function, okay, the ease of doing calculation is here. Okay. The ease of calculating m star, k star and the forcing function f star, it is easy here. Okay. But I am restricted to only one degree of freedom out here. Okay. If I have to choose y at some other point, then it becomes cumbersome. Okay. So, if I have to choose the maximum displacement, okay, this type of equations can be used. Okay. So, this is my choice of my shape function. So, instead of the deflection function, I am using this type of function. Okay. So, again m star, the parent equation I know, the parent equation is mass per unit length, then the shape function squared, okay, and integrated over the entire length. Again k star similarly will be EI, okay, differential of the shape function squared dx. Okay. So, using these two equations I can choose my mass and my stiffness. Okay. And here the ground displacement has been given as the forcing function. So, similarly this can be choose. Okay. Omega, the frequency of the system, it is nothing but k star divided by m star. So, I can calculate the omega also. Okay. And this is my equation of motion. Okay. Here what we could have also done is that in this particular equation the ground motion is the forcing function. Okay. Let us say if my forcing function was something like this, okay, then my f star would have become 0 to L forcing function as a function of the applied loading times the shape functions times dx. Okay. This would have been my forcing function, okay, if it is applied like this. Okay. So, depend upon the forcing function and spatial distribution, that is the distribution along the length of the structure, I can calculate my equivalent forcing function. Okay. Other points of interest here is the stiffness. Okay. So, look into the value of the stiffness. It has been given as 3.04 EI over L cube. I can derive it in other way also. Okay. The chosen degree of freedom is the horizontal displacement at this particular point. Okay. So, if I take a case of cantilever, okay, if this is my shape, I can calculate the deflection at this point. Okay. So, the displacement at this end point is PL cube over 3 EI. Okay. Now, I can rearrange them, 3 EI over L cube times deflection equals to my P, and if I use my definition of the stiffness, that is the force required to calculate a unit displacement, okay, then this becomes my value of the stiffness. Okay. The force required to cause the unit displacement, then this becomes my K equivalent. Okay. So, this is 3 EI over L cube, this is 3.04 EI over L cube. So, it depends upon the approximation of the shape functions. Okay. So, this way also I can calculate my stiffness. Okay. And mass also I can do the same thing. Okay. Mass also I can break down into two pieces. Okay. So, here if I lump it, it becomes m over 4, m over 4, m over 4 and m over 4. Since we are interested in this part only, it becomes m divided by 4, it becomes 0.25, okay, and this is 0.227, okay, again a rough approximation. Okay. So, even if we forgot or if we do a mistake in calculating the numbers, we can cross verify using this type of simple rudimentary checks that we already know using our statics knowledge. Okay. So, this type of checks can be applied to the things out here. Okay. So, the simple way to visualize a single degree of freedom systems. Okay. So, this is my equation of motion. Okay. So, what we did earlier, okay, we changed this system. Okay. We have a physical system, we choose a degree of freedom, okay, that was the deflection at this particular point. We choose a shape function, okay, we choose a shape. So, this was corresponding to first mode, okay, this shape was corresponding to the first mode. Okay. Then we formulated our shape function, okay, the numerator part is giving me the mode, okay, this is the shape of the mode, and the denominator part is giving me the chosen degree of freedom. I formulated my shape function, and from the shape function I calculated my m star, k star, f star frequencies and so on and so forth. Okay. In the previous example to that also we did the same thing. Okay. We choose our degree of freedom, that was the vertical displacement at center, and the shape was the first mode shape. Then we formulated our shape function, numerator part was giving me the shape, okay, of the mode, okay, that is this shape and it corresponds to the first mode shape, and the denominator part was giving me the chosen degree of freedom. Okay. This way we formulated our shape functions, and then we calculated our equivalent m star and k star. Okay. So, if we take any physical quantity, and for doing a single degree of freedom analysis, what we do is that we choose the degree of freedom. Degree of freedom we can choose at any point, and then depending upon the configuration of the structure, okay, cantilever, simply supported, fixed, okay, we choose the required mode. Okay. We choose the required mode. So, right now we are choosing the first mode, because we are assuming that the contribution of the first mode is maximum. Okay. So, then we are building the shape function, numerator part corresponds to the shape of the system, okay, in the first mode, and the denominator part is corresponding to the chosen degree of freedom. Okay. It is corresponding to the chosen degree of freedom. Okay. And that is how we are making our shape functions, and from the shape functions we are calculating our equivalent mass, okay, or generalized mass, equivalent stiffness or the generalized stiffness, and the forcing functions. Okay. Once we have those quantities, what we are doing is that we are changing this thing into a system having a equivalent stiffness, equivalent mass, and the equivalent forcing functions, and the chosen degree of freedom is the same out here. Okay. So, once we have that, we are drawing our free body diagram using D'Alembert's principle. We are writing the pseudo acceleration, thus equivalent stiffness, the equivalent function, okay, this is the chosen degree of freedom, and we are writing our equation of motion. Okay. So, we are writing down our equation of motion, and from the equation of the motion, okay, from the equation of the motion we are evaluating the response of the system subjected to the nature of the dynamic loading. From the response of the system we are calculating the maximum response of the system in the two phases, and then we are calculating the absolute maxima response. Okay. So, this is how we are going step by step. Okay. Okay. So, again same thing, okay, considering a simply supported beam that is having an elastic response, okay, we are taking the this mode shape, okay, this mode shape corresponds to the first mode. We are choosing the degree of freedom at center, okay, because this normally gives a maximum response when applied to a uniformly load. We are changing this thing into the equivalent mass, equivalent stiffness. Okay. So, first of all, a suitable deformed shape is assumed such that the displacement under uniformly distributed static load. Okay. So, normally what we are doing is that we are applying the blast load as a planar load. Okay. So, the shape will correspond to a uniformly distributed blast load. Okay. So, that is why we are taking the first mode, okay, which is represented by this shape. Okay. So, this will give me the numerator of the shape function. Okay. Then we are calculating the maximum response. Okay. So, the maximum response normally in this case will be at the center. So, we choose this thing as the degree of freedom. So, this will form my denominator. Okay. Then what we are doing is that we are evaluating the work done, strain energy and the kinetic energy of the beam, and from there we are writing the expression for the equivalent system as given below. Okay. So, we are writing the equivalent energy system. Okay. So, from the shape functions we are calculating the equivalent mass, equivalent stiffness and the equivalent forces. Okay. And from there we can write the different expressions for the work done by the external forces and work done by the internal forces. Okay. Okay. So, after that what we are doing is that we are equating the work done terms from the two analysis. Okay. And this becomes the definition of the equivalent load factor. Okay. The actual loading divided by the equivalent loading. Then we are equating the strain energy of the two systems and it becomes the equivalent stiffness. Okay. So, actual stiffness by the equivalent stiffness, and if we equate the kinetic energy then it gives the terms of the equivalent mass factor. Okay. So, here we are defining the equivalent load factor, equivalent stiffness factor and the equivalent mass factor. Okay. And the load and the stiffness factors are equal under the application of the static load, since inertia term is 0. If the inertia term is 0, okay, this happens during the equivalent static loads, then the equations of the motion brings back to the F equals to kx. Okay. That is for the static case. Okay. So, the static case, this is the equation. Okay. So, the dynamic equation of motion for the equivalent system, equivalent single degree of freedom system, okay, in terms of the equivalent mass and equivalent loading can be written in terms of here. Okay. So, what we also do is that we define a load mass transformation factor, okay, which is the mass term and the load term, the ratio of the mass and the load term. Okay. And then we can rewrite the equivalent single degree of freedom system, okay, in this fashion. Okay. So, what we did was we calculated the equivalent mass of the system, okay, we calculated the equivalent stiffness of the system, we calculated the equivalent force of the system, and from there we introduced the equivalent load factor of the system, okay, that is the ratio of the equivalent force divided by the actual force. We are equating the equivalent stiffness, okay, we are introducing a term called the equivalent stiffness, which is the equivalent stiffness divided by the actual stiffness, and this is the equivalent mass factor. So, it should be equivalent stiffness factor. So, equivalent stiffness factor is the equivalent stiffness divided by the stiffness, and equivalent mass factor, okay, that is the equivalent mass divided by the actual mass. Okay. Load factor, equivalent loading divided by the actual loading, equivalent stiffness factor, equivalent stiffness divided by the actual stiffness, equivalent mass factor, equivalent mass divided by the actual mass. And, okay. And after that we are rewriting our equation of motion in terms of the equivalent mass factor, equivalent stiffness factor and the equivalent load factor. Okay. And then we are reintroducing a term between the equivalent mass and the load factor, and we are rewriting our equation of motion. Okay. So, we will look into one more example, okay, where we will deal with a system, okay, and all this system are behaving in the elastic range. Okay. So, they are in the elastic range only. Okay. The properties of the system are, it has a length of 120 inches, okay. The load is given by 2000 pounds per inches. Okay. So, here we are asked to calculate the load mass and load mass factor, okay, and this is the distribution of the load. Okay. Now, remember here, in order to calculate the M equivalent and K equivalent, the magnitude of the force is not required. Okay. Only when we are calculating the effective equivalent forces, then only this magnitude will be required. Okay. Otherwise, for calculating the equivalent mass and the equivalent stiffness, we do not require the magnitude of the forces. Okay. So, now we look into the problem. Okay. So, we have been given a uniformly beam, okay, a simply supported beam, and the behavior, okay, what the behavior is required under a uniformly distributed some sort of dynamic load. Okay. So, these things can be approximated by a loading the beam uniformly with an equivalent static load. Okay. Okay. So, we can take this thing as an equivalent static load, okay, and then we can calculate the deflection equation, okay, for this shape. Okay. So, this is the shape mimicking the first mode. Okay. So, this is the shape function, okay, and this is mimicking the first mode. Okay. So, the numerator of the shape function, okay, if it is mimicking the first mode shape, okay, this curve, okay, then it can be given by the deflection equation, okay, caused by a uniformly distributed static load. Okay. So, this equation we can write down. Okay. Then if the required degree of freedom is at the center, okay, let us say we are interested in the maximum deflection. So, if we are interested in the maximum deflection, it will occur at the center. Okay. So, the chosen degree of freedom becomes the vertical displacement, okay, y vertical at center or at x equals to L over 2. Okay. Then this deflection equation calculated at y equals y at x equals to L over 2. Okay. So, that maximum deflection calculated at the center for this particular curve. Okay. So, this is my deflection function. Okay. So, the deflection function using an equivalent static load. Okay. So, the deflection function I am deriving by putting a uniformly distributed UDL static load. Okay. I can use the same nomenclature as P, or I can use some other nomenclature Sx also, but the point here is that this is just to cause this shape, okay, and this is mimicking the first mode shape. Okay. So, this is mimicking this mode shape, and the chosen degree of freedom is at the center. Okay. So, it is evaluated at y is evaluated at x equals to L over 2. Okay. So, this is the value of y at x equals to L over 2. Okay. So, this becomes the numerator, the mode shape, and this becomes the denominator, okay, denoting the degree of freedom. Okay. So, the shape functions will have two parts. It will denote the numerator as the shape function, numerator as the chosen mode shape, and the denominator as the chosen degree of freedom. Okay. So, this is how we formulate our shape function. Okay. So, once we have our shape functions, okay, we can use the equations, okay, for equivalent mass integration over the entire length, okay, mass per unit length times the shape function squared integrated over the entire length. Okay. So, this gives the equivalent mass, then equivalent stiffness, the flexural rigidity, okay, times the differential of the shape functions squared dx integrated over the entire length, and forcing function, distribution of the forcing function f x xi x dx integrated over the entire length. Okay. So, using these equations we can calculate our equivalent mass, equivalent stiffness and equivalent forces. Okay. So, if we can calculate this, then what was the use of introducing one more quantity, okay, load factor, mass factor and stiffness factor. Okay. What was the use of this quantities? Okay. So, let us look into the use of these quantities. Okay. Let us look into the easiest one, the mass factor. Okay. So, the mass factor is the equivalent mass divided by the total mass. Okay. So, here we can see we have a nice number 0.5. So, Km gives me a ratio between Me and M total, this is 0.5. So, M equivalent equals to 0.5 M total. Okay. So, what we were doing? We were analyzing a simply supported beam. Okay. So, as we have seen in the previous example, okay, what we can do is that we can use a discretized mass also in this particular case. Okay. If we forget anything, we can use a mass discretization also. So, what we will do is that we will break the beam into two parts. Okay. So, each part has half of the total mass. So, if we concentrate this at the nodes, okay, this will be m divided by 4, m divided by 4, m divided by 4, divided by 4. So, the total mass contribution at the center becomes m divided by 2. Okay. So, my mass equivalent, if I am choosing degree of freedom as at the center and the first mode, it should come out roughly as half of the total mass. Okay. And here after doing all this calculation, we can see that m equivalent is coming as roughly half of the total mass. So, we know that our calculations are making sense. Okay. They are fine. Okay. Now, okay. So, similarly we can check the stiffness factor and we can check the load intensity factor. Okay. These two factors similarly we can check. So, this is how the entire thing can be used. Okay. Now, we have to take into one more thing into consideration. Okay. All this analysis, the derivation of the equivalent mass, okay, they depend upon the behavior of the system. Here the system is required to behave in the elastic range, okay, when subjected to a dynamic loading. Okay. The entire response is to be in an elastic range. Okay. So, what it will do is that it will follow this elastic curve. Okay. So, this is the first mode shape. Okay. This is the first mode shape, this is the mode shape. Okay. This is the chosen degree of freedom. Okay. So, mode shape is this one, this is the chosen degree of freedom and the behavior is elastic. It means that it will follow an elastic curve. Okay. Now, we will look into a case where this becomes more than the elastic range. Okay. It goes into the plastic range. So, in the plastic range what will happen? The chosen degree of freedom is at the center only. Okay. Mode is in the first mode only. Okay. Earlier the shape of the curve was this type of curvilinear because it was in the elastic range. Now, the shape has become triangular because now it has been changed into the plastic range. Okay. So, all these three things plays a key role. Okay. So, the problem remains the same, the entire problem remains the same, but only thing is that the nature of the curve has changed. Okay. So, earlier it was in the elastic range, now it is in the plastic range. Okay. So, the deflection function is earlier it was given by an elastic curve, now it is being given by a plastic curve. Okay. So, x equals to x tan theta. Okay. So, this is giving my equation. Okay. And again it is being normalized with the x max, okay, that is the maximum deflection at the center. So, this is my degree of freedom quantity and this is my mode shape quantity. Okay. This is my mode shape which is again first mode, okay, but it is in the plastic range. Okay. So, again I formulate my shape function, okay, and from the shape functions I again calculate my equivalent forces, I again calculate my equivalent masses and again I looked into the equivalent mass and the force quantities. Okay. So, earlier my equivalent mass was 0.5, okay, in an elastic curve, now it is 0.33 for a plastic curve. Okay. So, this way using the load factors and the mass factors we can cross verify our calculations. Okay. So, this curves, okay, we can use to calculate our equivalent stiffness, our equivalent mass, okay, and the load factor, mass factors and the load mass factors. Okay. So, choosing different type of configurations. Okay. For an elastic case we can calculate our load factors, we can calculate our mass factors and we can calculate our load mass factors. Okay. So, in earlier slides what we did was we saw the derivation of these quantities. Okay. Now, all these quantities are been given as a ready reference chart. Okay. So, this ready reference charts can be used to calculate the different quantities. Okay. In the when the system is remaining in the elastic range and when the system is remaining in the plastic range. Okay. So, these are the ready reference charts that can be used. Okay. So, for a uniformly distributed load and for a different type of structures with different loading conditions. Okay. So, this type of charts can be used as a ready reference. Okay. And then as an exercise what we can do is that you can try to calculate this factors also, okay, and cross check using your own calculations. Okay. The equations, the methodology has already been provided to you. Okay. So, this all the things can be cross checked. Okay. Okay. So, again for different type of system having different mass distribution, the load factors, mass factors and load mass factors can be used. Okay. So, again uniformly distribution systems, cantilever systems, okay, all the quantities have been given as a ready reference charts which can be used for the design and the analysis purpose. Okay. Again system having fixed at one end and a cantilever at other end, okay, that is the propped cantilever. Okay. So, a propped cantilever system, we saw a uniformly distributed system, okay, a simply supported uniformly distributed system, a cantilever system, now we are seeing a propped cantilever system. Okay. So, for all these systems the different load mass factors are being evaluated. Okay. Again the same things follows. Okay. So, all these charts have been prepared for different boundary conditions and when the system is subjected to different cases of the blast loading. Okay. Keep one thing in mind, the equivalent mass and the equivalent stiffness, okay, is not going to change, okay, depending upon the nature of the external loading. Only thing is that the treatment of Fe might change. Okay. But when the system is subjected to a loading, okay, and if the same mode shape and same degree of freedom is chosen, okay, let us say in these two cases, okay, let us say in the case of a simply supported beam. Okay. So, in the case of a simply supported beam subjected to UDL load and a simply supported beam subjected to a point load. Okay. In both the cases the equivalent mass and the equivalent stiffness will have the same values, okay, because the frequency of the system cannot change depending upon the externally applied load. The frequency is not a function of the externally applied load. Only thing is that F equivalent will change, but the mass equivalent, K equivalent and the frequency of the system will remain same. Okay. It will not depend upon the externally applied loading, the nature of the externally applied loading, but it will always remain same. Only thing that is going to change is the F equivalent. Okay. So, that is why the different configuration having different types of loading is also shown, because the F equivalent is different in the cases, okay, not mass equivalent, not stiffness equivalent, because these are the eigen quantities and they do not depend upon the application of the load. Okay. Unless and until the shape function and the chosen degree of freedom is same, the mass equivalent and the stiffness equivalent will be same always. Okay. So, these are the different cases. Okay. So, from here I stop today. I again ask you to practice this thing, derivation of the mass equivalent quantities, derivation of the stiffness equivalent quantities, derivation of the force equivalent quantities, and the ready reference charts has been given to you. You can cross check with them and verify with them. Okay. Good luck. Thank you.